Now we can make things a little bit more complicated. Let's say that we're going to fire something with some initial velocity v0 at some angle theta, and now we're going to have it land at some different height h. Okay, so if we do this, we see that we can't use the range equation that we solved for before, right? Not only, so we can't use Vy is equal to minus V0y equals V0y minus GT, because now that would only apply if we had kept going all the way back down to the same height. But now we don't know how much time it's going to take to get to here. So we need to find it a different way. So before you go and get crazy and start trying to use the y equation that's going to be quadratic in t, remember that we still have another equation that we can use, which is x minus x0 is going to be v0x times t. And so this is going to give us the time to arrive back at that height, which is going to be x minus x0 over v0 cosine theta, which is going to be r over v0 cosine theta, where r is this distance. Oops. Oh, that was very poorly drawn. Right, so now we've been able to find the time. Okay, so now, again, we want to try and find, so let's say we want to find what the velocity is, what velocity we need. So we're firing at an angle theta. We want to get to a height h. We know the range r, and we want to find out what is our velocity needed to do that. Okay, so now if that's the problem, so we've got our equation for time. Then we can say that h is going to be y0, which is 0, plus v0y, which is v0 sine theta, times t, minus 1/2 g t squared. But we've already found t. So we know that h, so the v0s are going to cancel out when we multiply by t. So we'll have an r tangent of theta, and then a minus 1/2 g times t squared. So r squared over v0 squared cosine squared theta. And this is equal to h. And so from here, we can multiply by 2v0 squared cos squared theta. And so we'll rearrange terms a little bit. We'll say that 2v0 squared cos squared theta is multiplied by, we'll pull this over to the other side, so we have an h minus r tangent of theta, which is going to equal g times r squared. So now we can divide by everything and take a square root, so we see that v0 is going to be the square root of g times r squared times h minus r tan theta, all divided by 2. Oh, I'm sorry, this is not right. It's g times r squared divided by 2 cosine theta times h minus r tangent of theta. And so this would be the velocity that we need to fire to get to that point. We could simplify this a little more. We can pull in the cosine of theta, so we have g r squared over 2 times h cosine theta minus r sine theta. And we check to make sure the units are right. So we have meters per second squared times meters squared divided by meters, and take a square root of that so we have meters per second, so we get the right units for velocity. And so notice this is a little bit more difficult because of the fact that we're going to a different height than the one that we started at. But you could have this same exact problem, but they could be doing something else. They could be asking you, what is the range given, these other variables, or what is the height given some of these other variables, or the angle, or, it just depends on what variables they give you and what you're solving for. But the procedure is exactly the same, no matter how you're doing it. And so now in the next video, we're going to take a look at what happens if we start combining these projectile problems with problems from like earlier in the class, like conservation of momentum.